So question 3 is a required practical question. So this is one of the practicals that you know that you could be asked questions about in your exam, and here is an example of that working. So in this specific case, we're looking at the specific heat capacity of aluminium, and first of all we've got to draw a labelled diagram showing the apparatus that we would use to determine the specific heat capacity of aluminium and how that should be arranged. Okay, now there's a couple of different permutations that you could use for this, but regardless of that, most of what you're going to need is exactly the same. So this is something you should have seen or you should have done yourself. So remember, we have got a specially prepared aluminium block, okay, which has got 2 holes drilled in it already. So there is one into which we can place a thermometer, and there is another slightly larger one into which we can place an immersion heater. Okay, so that immersion heater will need to be connected to a power supply. So I'm going to indicate my power supply over there with this symbol here. Okay, so I will need to connect that up there and there. Okay, so I would start labeling this up. I've got my aluminium block, I have got my thermometer, and I have got my immersion heater. I've got my power supply. Okay, other things that I would have, okay, my aluminium block, I would need to have a layer of insulation around that just to stop some of the heat escaping, as the hot block otherwise will transfer some energy to the surroundings. So I'll be looking to see a layer of insulation around the block as well. Okay, now in order to calculate the specific heat capacity, I'm going to need to measure the temperature rise. I'm going to need to do that over a period of time. So one way in which I could measure the time is to have a stop clock, although that's not particularly essential here. Okay, I'm going to need to know the mass of my aluminium block, so I could draw a balance for measuring the mass. Okay, but that's not critical either. We can write about that in a method we're going to do later on. Okay, what is critical is that we also need to know the amount of energy that we've supplied to the block. Okay, now there are 2 different ways that we could do that. Okay, first way we could do it is we could connect a joule meter to the power supply so that we can directly measure how much energy has been supplied to the block. Okay, the second way that we can do it is indirectly. Okay, if I have an ammeter, I can measure how much current is being supplied, and if I have a voltmeter, I can measure the potential difference, and multiplying the potential difference by the current will tell me the power. So if I also know the time, I can work out the energy that way. So either I measure the energy directly with a joule meter, or I have an ammeter and a voltmeter, and then in my method I'm going to mention that I'm using the readings of the current and the potential difference to work out the power. Right, and then in this part of the question we're going to describe how we're going to use the apparatus. So we've got our diagram, so we can make reference back to our diagram, and we've basically got to explain what we're going to do in order to calculate the specific heat capacity. Okay, so things that we'll be looking to see in the method. First of all, we'd want to talk about how we're going to do the calculation. So the equation that we're going to be using is that the energy we supply is going to be equal to the mass of the block times the specific heat capacity C times the change in temperature. So I'm using delta theta there to represent the change in temperature. So in order for me to calculate the specific heat capacity, I'm going to need to know the energy, and then I need to divide that by mass and also by the change in temperature. Okay, so I'm going to set up the equipment as I've shown in my diagram. Okay, I'm going to need to know the mass of the block, so I'm going to use a mass balance so that I accurately know the mass of the block. I've got my thermometer so that I can accurately measure the temperature rise of the block as I'm supplying it with power from my power supply. Okay, the way that I drew my diagram there is I had the ammeter to measure the current, and I had my voltmeter to measure the potential difference, and then I can work out the power by doing the current times the potential difference, and then I would need a stop clock or some other means of measuring time so that I could then work out the energy by multiplying the power by the time. Okay. Alternatively, if I'd drawn a joule meter in my previous diagram, I could simply say that I was using the joule meter to directly measure the amount of energy I was supplying. So whichever way we've done it, I need to know the energy, and I need to know the mass and the temperature rise. Okay, with all of those things in place, we could do that procedure and obtain a result. Okay, be worth pointing out that we probably wouldn't just do the experiment once and hope we'd done it right. We'd want to repeat the practical a number of times and then take an average of the values we obtained so we get a better estimate of what the true value is. Okay, we could also talk about safety aspects. So the immersion heater is obviously going to get hot, so we wouldn't want to touch that with our bare hands. We'd either want to use some protective gloves to handle it, or we just want to leave it alone until it's cooled down. Okay, so I think all of those things put into there would give you the full 6 marks as long as they were laid out in a logical order. 3.3, the final part of this question, suggests that whichever method we might have used, we'd probably end up with a value that is bigger than the actual value. Okay, and it's our job here to explain why that would actually be the case. So if we look back at the equation we were using, the specific heat capacity would be equal to the energy divided by the mass of the block multiplied by the temperature rise. Okay, now the simplest way to explain this, I think, is with whatever amount of energy you supply, not all of that energy is going to directly raise the temperature of the block, because the block will be hotter than its surroundings, so therefore it will transfer some of its energy to the surroundings, so we won't get as big a temperature rise from a certain amount of energy as we would if there were no losses at all from the block. Okay, so as a result of losses, as a result of the hot block transferring some of its energy to the surroundings, the temperature rise that is produced is smaller, and therefore because we're dividing by something that's smaller, the value we'll get for our specific heat capacity is larger than it ought to be. Okay, so not all of the energy is going into heating the block. Some of that energy is also being used wastefully to raise the temperature of the surroundings.